Okay, so we should be recording, and then let me hand things over to the Helio-One group.
All right, let's start. Good morning, everyone. This is the presentation for Helio-One heliostat module. Our group number is 632C, and our section 17243 in the custom project class. Our team members are composed of Ronnie Alima, the reflector assembly lead, Dario Calle, the electronics and controls lead, Daniel Espinosa, main control box lead, Christian Jacom, myself, main control mechanical lead, Thomas Gallagher, mechanical assembly lead, and Wen Shizu, reflector control box lead.
Our value proposition focuses on the team's diverse skill set and backgrounds, contributing to our unique ability to combine precise actuation methods with modularity in order to achieve the highest quality product. Although motors were utilized in rotating our heliostat in both directions, we still discovered a new low-cost design to reflect the same amount of light larger current configurations provide. Since we believe gears were the best way to achieve our goals, we manufactured our very own set of planetary gears in hopes to reduce costs. Other than being remote controlled, self-homing, and weather resistant, Helio-One's main aspect that sets it apart from commercial grade heliostats is its small ecological footprint. Helio-One's goal is to reflect 98% of the light it receives back to a central location. This is the highest percentage the Mylar film will allow us to achieve. High precision motors in tune with 4:1 gear reductions allow us for smooth adjustments. In particular, NEMA 17 motors are used in the 4 quadrants, and one stronger NEMA 23 motor is used to rotate the entire top half around its center of gravity. Helio-One's design mitigates shading issues and also proves to enclose all electronics throughout its internal wiring channels. Furthermore, the symmetry of Helio-One's design also improves stability by allowing itself to always be balanced despite its orientation. The size is compact by almost being a meter tall by a meter wide.
Some key features of the Helio-One is that it has a 359 degree rotation on the azimuthal axis. This is powered by the NEMA 22 motor, and the resolution of each step is of 225 thousandths of a degree. Also, the reflector assemblies also share the same resolution, the same step resolution, and they have 90-degree rotations.
The module is comprised of 4 main subassemblies: the structure, reflection, main gears, and main control box. We will now discuss each of these subassemblies in greater detail. The first subassembly to discuss is the structure. The structure is made of CPVC tubes, which are assembled into a tree-like configuration as seen in the images. Known for its low thermal conductivity and high stability, the CPVC material chosen for the structure protects the internal components from the environment and increases the lifetime of the module. Wiring is run all throughout the entire structure as seen in the images. 2 sets of wires come from each reflector and go through a hole at the end of each PVC branch. 1 set of wires comes from the limit switch, which tells the system where to hit home, and the other set of wires comes from the motor, which controls the rotation of each reflector. Wiring for the real prototype was carefully done through the use of heat shrink tubes and labeling each wire group stemming from the respective reflectors. From 5 limit switches and 5 motors, a total of 30 wires were run through the entire structure, leading all the way to the control box.
Next, I will introduce this reflection subsystem of the heliostat. The Helio-One are made of 4 reflector assemblies. Each reflector consists of a Mylar mirror, a backing, and a reflector control box. And the control box, the backing is a plastic plate with a press-fitted ball bearing in the middle. And then the control box is a small metal box made of 18-gauge aluminum sheet metal. It is tightened up by 4 rivet nuts. Inside each reflector control box, there's a NEMA 17 stepper motor, which controls rotation with a 4:1 gear ratio.
Now I will explain and show more about the main motor and gear set rotation. All connections must flow through the subassembly without obstructing rotation. From a bird's eye view, the planetary gear assembly includes a sun gear in the middle, which is directly attached to the NEMA 23 stepper motor on the other side of the motor mount. 3 planet gears are used to translate the motor's torque to an outer ring gear that is hard to see from this angle, but it's sitting flush with the hubcap that is adhered within to. 3 larger holes are required to allow wiring to travel from the control box up into the tree. Azimuthal rotation has the same 4:1 reduction ratio as the reflection assembly on the upper motors. I added this slide to show in further detail how the heliostat can orientate itself in the azimuthal direction, or in simpler terms, how the limit switch works. Unlike the other 4 limit switches which find home when they are pressed, we use the same limit switch but in reverse, meaning it is released when it is home. This only requires a little tweak in the code, but for 359 degrees, the limit switch is actually being compressed downwards by the ring gear and only releases when it finds the ditch within the ring gear from either direction. Creating the sloped edges or walls of the gully was not possible on the CNC machine, but a bunch of sanding made it possible for the roller to easily roll in and out of the gully without jamming or breaking.
So talking a bit about the manufacturing a little bit, one of the most unique characteristics that we have in our module, it's actually using casting gears that were done by the casting manufacturing method. We use a tabletop furnace in the lab to melt aluminum scrap material that we have with the lab, and we build this 3 planetary gears. As you can see on the first image, that is the first thing after solidification happened within the mold. The second gear shows the 3 gears and actually shows the one in the middle, a little air bubble that stayed within the mold. So that was one of the things that we had to discuss about. And then the third image shows all the planetary gears with the ring gear that was sent to manufacture using exometry, and the gear housing showing how they interact with each other. Once again, all these gears were done using scrap aluminum, which basically brought the cost of the prototype in lab to 0 for these gears, compared to over $120 that were quoted on exometry.
Now I'm going to talk about the main control box. The main control box is made out of 16-gauge steel sheet metal, and this is where most of the electronics are in. And the main control box complies with the IP55 standards with the aid of a pipe grommet and a rubber trim that helps seal the box. Also, as you can see here, the representation of our first control circuit. And also in the main control box is where you will find the 30 amp power supply and the TV6600, which is a driver for the NEMA 23 motor, and the microcontroller, which is a ESP32.
So the heliostat achieved movement through 4 A4980R stepper drivers, 1 TB6600 stepper driver, and the circle that shows the ESP32 microcontroller. On the top left corner, we have a 12 to 5 volt converter, which removes the need for 2 different power supplies. Normally, 2 power supplies are necessary since the ESP32 microchip requires 5 volts to power itself, while the stepper motors require 12 volts for movement and between 3 to 5 volts for signal handling. This is an image of the wiring schematic made using the software Eagle from Autodesk. The main idea behind this design was to keep everything as close to symmetric as possible, while also working around the fact that some of the pins on the ESP32 are input-only pins. The most challenging part was figuring out the runs for the power delivery lines, since all 5 drivers needed 3 volts for signal handling and 12 volts for powering the stepper motors. On top of that, it is also recommended to have separate grounds for different voltages. So after combining all these requirements, this is the most optimal way we found that could get the job done and allow enough space to solder the routes without any shorting. This is an image of the final product after all the runs were soldered in place. Keep in mind that this image was mirrored about the vertical axis since I was looking at the pins of each chip from the front. If you look closely, you might be able to see one of the best features of this design. The microchips are not soldered in place. Instead, what is soldered to the PCB are adapters. This allows us to hot swap any of the chips without much effort if they stop working for some reason. The same thought process was used for the pins where the stepper motors connect so that they're easy to switch or repair if the need arises. In this view, we can also see some resistors, which are used as pull-down resistors to make sure that all the switches are reading 0 unless pressed on purpose. Finally, 2 start capacitors are used to provide the motors with a large initial power to move them without any unintended delay when a command is given. Here are some snippets of the code created to control the heliostat. Some key details about the developing of the program are that the program uses 2 different libraries to control the stepper drivers. The 4 A4980A stepper drivers use a library called A4980A, and the TB6600 uses a library called Accel Stepper. Another key detail is that the main code, which you see a portion of it here, was designed to take care of receiving the commands and handle group functions to complete the commands. However, the bulk action is happening behind the scenes in these 2 files that have been imported into the main file, the left stepper.h and the as stepper.h. These are small portions of the code that I mentioned is imported into the main file. The files are known as classes, which allows us to have as many stepper motors as the memory can handle on the ESP32 chip, each with their own variables without having to write the whole code multiple times. All that is needed to use the class name, all that is needed to use the class is the variable type, pass the parameters for what pins on the ESP32 are being used for the stepper, and that's it. The stepper will be fully functional. On another note, I'll give you a description of what is happening in each of these functions. The homing sequence function, when called, stores a timer, and while the time that has passed is less than the time to wait variable given, the stepper starts to move at 30 RPM until it finds the limit switch, or the time runs out. If it does find the limit switch, then it will rotate 10 steps in the opposite direction, and then look for the limit switch again at a speed of 5 RPMs to minimize errors. After the switch has been homed, it will make the current position be the 0 position. Now, the move motor function for the elevation steppers. Something cool about this function is that a digital limit was implemented using the home position and the expected number of steps the stepper motor should rotate. For example, if the command given to the driver says to move the motor 401 step, it will simply return a message that says out of bounds, so that the users know that he's asked the motor to rotate more than he should. However, if the movement is below the limit, then the stepper will simply rotate for the steps indicated and at the speed given. Once completed the motion, it will return its current position so that the user knows where the stepper is with respect to the home position. Now, the function for the SC stepper class does the same thing, but I included it here so that you could see the difference in syntax used by the A4980A and the Accel stepper libraries. Main difference being that the A4980A library uses a number of steps to move, while the Accel stepper asks for a location to move to.
All right, so on this section, we're going to talk about the engineering analysis and calculations that we did on the module to validate the design. Starting with some stress calculations. This calculation represents the stress that the CPVC arms of our module experience under the weight of the complete reflection assembly system. This is one of the most critical areas that we saw in our design because our CPVC tubes are extended throughout the entire length of the arm. However, at the very end of it, we connected to the ball bearing and to the control box, which it's actually given all the weight from the reflection assembly, control box, NEMA 17, and gears, which turned out to be 4.75. We calculated to be 4.75 kilograms. So in here, we're using a simplification for the hand calculations that we did of a cantilever beam, where we apply the force of 4.75 kilograms times gravity over the length of the CPVC pipe, and it's fully constrained at the other end, meaning that, or because we glued this with PVC glue, which bonds the CPVC tube to the PVC T-joint. In this case, as you can see, the first equation, the sigma max, we show this the maximum stress that we can find using a cantilever beam, where Y is the center of neutral axis. In this case, would be the outer radius of the PVC, of the CPVC tube. M max is the maximum moment. That's going to be depending on the force that we apply at the opposite end. And I is the moment of inertia. I also give the diameters in here of the CPVC tube that we're using. As you can see, after calculating, we find that the maximum stress at the tip of the connector of the PVC is 12.68 megapascals. Our factor of safety required based on a customer need, it's a factor of safety of 2. In this case, CPVC was found that about the yield strength is 51 megapascals. And so therefore, using the calculation, our factor of safety is actually 4.07 in this situation. We also put this in terms of a margin of passing. We have a margin of 3, meaning that we can, after the factor of safety that they gave us, we have 3 times more of passing, meaning that our structure can be said to be safe. Additionally to this hand calculation, we also run a small FVA analysis to give a higher level of confidence in our answer. And after doing the analysis, very simplified analysis on the PVC tube, we find that the maximum moment that we've achieved on the connector, it's 12.76 megapascal. And the one that we find using hand calculation is 12.68, which is very close, meaning that we do have confidence in our answer. Going forward, we also did the same analysis of stress on the 45-degree Y PVC connector. As you can see, we're using the exact same formula. Nonetheless, for the maximum stress, we are multiplying this by the angle where the force is acting. And we find this stress to be 17.48, slightly higher than the other one. Nonetheless, our yield strength is still 51 megapascals for CPVC, which give us a factor of safety of 2.95 and a margin of 1.95, which can be said as stable for passing. And so our structure is also considered to be safe in this direction. Another extremely important analysis that we run is about wind conditions on the reflection assembly. If we think about it, we have basically a 0.5 by 0.5 meters square of sheet metal that is being compressed by or in tension by the wind. And so this can easily snap off. So basically, to perform this analysis, we consider this wind speeds to be the average wind conditions in Gainesville, Florida. The average conditions are considered to be 18 miles per hour and a temperature of 293. We calculated, to be very precise, the density of the air at this temperature and found the force of the wind acting over the area as area where the wind contacts, the density of the air, and the velocity, which turns out to be 20.66 newtons. After this, we find this expression called P wind, which is actually the force of the wind per unit length that we have in our system, which turns out to be 40.91 newtons per meter. And then using the expression of a cantilever beam, once again, considering the worst case scenario as the extreme, as one of the extremes of the mirror, we find this to be 1.2 Newton meter as the maximum moment over the entire length. Using, again, the maximum stress of a cantilever beam, we're able to find the stress as 49.84 megapascals on the brackets, in this case, on the restricted end. And we use von Mises criteria for failure criteria, in which we use the sigma maximum as bending plus sigma tension. However, sigma tension, the magnitude of sigma tension was megapascals times 10 to the negative 3, whereas our sigma maximum due to bending, it's actually 49 megapascals. So as we can see, after finding von Mises stress up to the second decimal, the answer remains exactly the same as sigma max. The only difference is on the third decimal, which of course we didn't include, and rounding was not enough as to make it go up. Now, once again, comparing this to the yield stress of the material we selected as aluminum 7075 T6 of a yield stress of 570 megapascals, we can say that our structure is safe, considering that we have a margin of over 10 points and a factor of safety of 11.43, which we can be thinking that this is over designing, and considering that the customer requirement is a factor of safety of 2. However, the reason why we had to pick this material, it's explained on the following slide. Before we go there, we also run an Fva study to validate these results as we did before. And as you can see on our Fva study, we end up with 55.53 megapascals compared to the 49.84 megapascals. It's a little bit less than 10% difference. However, comparing the results and with this confidence that we have on our hand calculations, we believe that the numbers are correct. Now, to go and explain the factor of safety or why the factor of safety is so high, we can go into the next slide. And in here, we show that we also consider extreme weather conditions, as we are located here in Gainesville, Florida. We know that there's a lot of hurricane season in here, so we understand that our modules should be able to withstand at least tropical storms or Hurricane 1 wind speeds. We found that an average category 1 hurricane is about 95 miles per hour. So we did the exact same analysis, but with a different wind speed, and we find that our force of the wind increases to 204.69 newtons compared to the 20.66, about 10 times more than average conditions. We run the exact same analysis, and we find that our sigma von misses for failure is 493 megapascals now. Now, comparing it to the 570 megapascals yield strength of aluminum 7075, our structure is only moderate because we're still not failing, we're still not under yield. However, our factor of safety now, instead of being 2, it's only 1.15 under these extreme conditions, and our margin would be 0.15 as named as critical. We are not too concerned about this issue because this analysis is assuming that the Hurricane 1 wind speeds are acting completely perpendicular to the mirror, where in reality, our module would go in a safe mode, making an ideal case where the wind flows completely parallel to the mirror. And then the thickness of 18 gauge sheet metal would not allow enough distances for this to give enough stresses for the structure to deform. So even under worst conditions possible, we're still passing with a moderated structure, but we show that our factor of safety is at least over 1 in this worst condition case.
Now I'm going to talk about the heat transfers analysis. We did heat transfer analysis to ensure that the electronics inside the heliostat will not, the temperature of the inside the heliostat will not surpass the operating temperature of our electronics. So for the heat transfer, we use the first law of thermodynamics and make some assumption, and we make the assumption that we're a steady state. So the change of energy with respect to time will be 0. And since we also have reflectors that provide shade to the heliostat itself, then we assume that the energy from radiation from the sun is also negligible. So Q in is also 0. So after making those assumptions, we just find the work performed by the work that the motors receive, meaning the energy, and then the work out. After we get our Q out, we also calculated the coefficient of convection, and with this and with the second line, we were able to determine temperature of inside the control boxes and the reflector boxes. So as you can see here, inside of the control box, we will expect a temperature of 50 degrees Celsius, and inside the reflector boxes, we will expect a temperature of 79.5 degrees Celsius, which is less than the maximum operating temperature of the electronics. Another requirement for Helio-One was that it had to meet the IP55 criteria. So we did IP55 testing on the heliostat. In the first picture, you can see when we did the testing for the particle infiltration, which we spray baby powder according to the standards for IP testing. And then after the test, we swipe a cloth on the inside of the housing, and then we only get a 0.5% increase in the mass of the cloth. So that means that barely any dust came in, and that means the standard for the first 5. And then for the second 5 is for the water filtration test. And again, using a test setup specified by the IP standards, we spray the control box and the reflector box with water, and then we use indicator tape that will turn red if the water touches the tape. And as you can see in the pictures, the tape still remain white, which means that they didn't came in contact with water. So this with these 2 tests, we can we are 100% confident that the prototype meets the IP55 standard.
Here are a couple of videos showing the real prototype testing. The mirrors were covered with a pink plastic film in the middle video to protect them in the lab, but this film was later removed when testing at the UF Solar Park. The videos show control of each reflector independently, as well as the control of the azimuthal rotation of the entire module. The result of testing at the solar park was that the module achieved a maximum focal thermal power of 988 kilowatts by shining 2 out of 4 reflectors at a very small target sensor. Given the proximity of the heliostat to the sensor, an ideal situation for testing would have a larger target where all 4 reflectors can hit the sensor at once. It's estimated that the module would realistically have a focal thermal power of 1.98 megawatts, which is nearly double the power of the sun alone. Here's the cost breakdown for the Helio-One module. On the left side of the table is the real cost for building our prototype, in which we incurred costs for ordering off-the-shelf parts, as well as custom manufacturing certain parts. This came out to $713 total. On the right of the table is the estimated cost breakdown when considering a bulk production of 3,000 modules. Bulk orders consider discounts for partnerships with manufacturers, as well as discounts on shipping due to high volume. This cost breakdown includes additional estimated costs for manufacturing and assembly labor. The total estimated cost for bulk production is $344 per module.
So in our design, each heliostat could rotate 180 degrees individually. The calculated lifetime of Helio-One is 20 years. The area of each heliostat is 0.25 meters square, and there are 4 of them in total. The structure minimizes the shuttling all the time. From the calculation, all the critical factor of safety is greater than 2. And from the prototyping test, all the critical component passes the IP55 test. And our Helio-One has a total reflection area of 0.998 meters square. The prototype cost is $700. Input power is 1.98 million watts. The solar concentration ratio is 1,063 cents. The allowable rotation degree is 359 in major axis and 270 in minor axis. And 74% of our heliostats are OTS parts. So among all these customer needs, there's only one that we actually did not able to reach.
Although things always look better on paper, there were still some problems that affected the performance of Helio-One. One being the 3D printed gears we used in the reflection assembly started to wear faster than expected in the outdoor heat. This appeared to cause some slipping until some teeth ultimately sheared. A solution to this would be using all metal gears. A second thing would be the placement of limit switches in the reflection assembly need to be in the correct orientation, or else they will break off from being hit from the wrong side. A solution to this would be careful when assembling delicate parts and make sure they're in the right orientation. 3 is the friction from our grommets in the reflection assembly were created too much friction for the NEMA 17 motors to overcome. In our final test, we had to sacrifice being IP55 certified just to get the mirrors to turn. A solution to this would be finding O-rings with less friction or using a stronger motor to fight off the friction. 4 is each mirror needs to move independent to each other to maximize concentration of light to a certain area. A solution to this would be a minor coding adjustment that sends different steps to in particular quadrants. 5 would be the holding torque of the mirrors is simply not enough to withstand high winds. A solution to this would be using counterweights on the back of each mirror to help reduce the amount of load each motor needs to withstand. 6 is overheating not only melts our plastic components, but quickly could fry our circuitry, in particular the motor drivers. A solution to this would be better heat transfer inside the control and reflection boxes. And 7 is staying under budget. With a $100 goal, we quickly realized how unlikely it was to stay under this given how many motors and gears we used. And a solution to this would be shaving off some extra weight and reducing the stock size of metal components to allow for a cheaper cost. And here's most of our group at the solar park with Helio-One testing day. Thank you for listening to our presentation. Please feel free to ask any questions or leave any comments. There's additional heat, structure, and wind calculations after this upon request, and thanks again.
We now want to open a panel for possible questions and answers. That the team can answer.
Yes, this is Tom Singer from Northrop Grumman. A couple of things. I'm not going to talk about the FEM because I talk about the FEM all the time and I get tired of it. I appreciate that you at least had hand calculations there, but can we go back to the slide where you're actually showing the structural calcs?
Yep.
So I like that you had a margin of safety calculation, which is sort of what I'm used to looking at.
Mhm.
But I'm wondering how you calculate it, because the typical way, it seems like you calculated that against the limit load rather than the load with your required factor of safety applied.
That is correct. We
so
calculated the
usually-
margin as based on the yield of the material. So how much we're
Yeah, so
passing
you,
from
so
the
you would
yield.
take your 51 MPa divided by your 12.68 MPa, subtract 1, and that's what you're calling your margin.
That is correct.
So usually you would apply the required factor of safety to the load that's occurring at limit, right? So here you would do 51 MPa divided by 2 times 12.68 and then subtract 1 from that.
Okay, that makes sense.
But I do appreciate that you're thinking about margins, because maybe finally people are reading my notes, because I write about that every time. I'm curious. This was your maximum holding stress calculation. So what load were you coming up with as your driver here?
Yes, so we actually have a load of 4.75 kilograms. That is accounting for the small control boxes, the NEMA 17 motor, the 2 gears, the ball bearing, and the mirror backing.
So is that just the weight of the structure?
Absolutely, yes, that's just the weight.
Okay, so if you're showing a analysis of that pole, that beam, that's not going to be the critical load, right? I mean, you did an analysis on the next page. I think you were considering wind loading on things. I'm curious why wind loading isn't going to be your critical condition here rather than weight, or weight plus wind loading.
Well, so the critical, both are critical. The difference is that the wind is critical on the 90-degree brackets that are attaching the backing of the mirror. But wind is not really critical in this sense, because whenever wind would happen, once again, we go in the safety mode, in which that would be hitting the mirror on the side, which we will be hitting our contact area.
When are you going to go into safety mode? Like if the wind is 5 miles an hour, do you have to go in safety mode?
Oh,
If the
no,
wind
safety
is
mode,
20 miles an
it's-
hour, do you have to go in safety mode?
Correct. So safety mode, it's actually going above the average conditions, which is 18 miles per hour.
Okay, so where's your 18 mile an hour wind load on this?
That is not the calculation here. That is the wind calculation. Can you go 2 slides? One more. Oh, sorry, that one.
Right, that's your stress analysis of your reflector surface, but where's that being reacted? Like, what's holding up the load that's acting on the reflector surface? That's on that pole, correct?
I see what you mean. Yes,
Okay,
I see what
yeah.
you mean. Absolutely.
Okay,
Yeah, we're missing
All
the
right.
Actually,
force of the
on-
this force of the wind.
yeah. All right, so while we're looking at this slide, we're talking about a force from the wind is 20 newtons for an 18 mile an hour wind. And then on the next slide, you had a force for the wind of, what was it, like 200 newtons for
200
a
and-
95 mile an hour wind.
Yep.
Right. I'm not really an aero guy. I'm more of a structures guy. But I'm pretty sure that drag force goes with the square of velocity, right? So if we multiply velocity by 5, more or less, I'm expecting the drag force to go up by a factor of 25, and that's not what I'm seeing.
Okay.
There's also an issue. This is Isaiah Hendrick from Northern Grumman. You guys go back to that last slide. So no, last slide.
Previous.
with the wind
Previous.
load.
Previous slide.
With the wind load. Okay, so you guys have a 20. This is kind of like on Tom's point. So you guys have a wind load of 20.66 newtons. So where did you get this equation from? Because last time I checked, area times density times velocity is mass flow rate, not force. Because you're dimensionally working out to kilograms per second. Like if you do the dimensional, I just did, you do the dimensional analysis, you're getting kilograms per second. So how are you getting a force from that without applying momentum equations or something like that?
So this force, so this equation was found on this equation we actually found it online on a reference that we have.
But does it make sense, like dimensionally, right? Like did you guys?
Yes,
look at the
I
units when
totally
you were doing
understand.
this?
That would be Newton second, if I'm not mistaken.
I think you're correct. We made an error.
Yes.
Yeah. So check that. Let's see. I think you had mentioned that you were generating like 900 kilowatts of energy, or focusing 900 kilowatts of energy on something.
Yep, that is on the at the end of the slides. Can you go?
I mean, you'd have to be much closer to the sun than Earth is, right? You've got about a meter of reflecting surface, and best case we get 1,000 watts per meter squared at Earth's surface, right? So I'm curious how you get more than 1 kilowatt.
Daniel, can you actually go to the slide 37? That's where it should be. There we go.
Yeah, fundamentally, I think you might have a unit error here where there's like an extra factor of 1,000 in here, because I mean, you're not going to get 900 kilowatts with a 1 meter squared reflecting area.
Correct. So the reason why we have 1.98 megawatts, it's because that is accounting for the whole field of heliostats.
Mm-hmm.
We actually achieved.
But you, I think back when we were talking about like your performance of this one prototype, I think the number was 900 kilowatts.
Yes, that is correct.
Was that an error? Was that supposed to be 900 watts?
We actually measured that with a sensor on the video that we were showing on the field. We actually measured not that on the sensor. However, we did get some reflection from the ground. So at about 200 kilowatts. So we are looking at our total reflection on the sensor of about 900, but that's including about the 200 kilowatts.
Yeah. I think it was watts.
So JVN is 988 watts per meter squared instead of kilowatts, right? I mean, that's a reasonable number, right?
Yep.
So make sure that is correct. You on your cost slide, were you breaking down your cost? Yeah, here we go. So you're estimating that you're going to reduce your off-the-shelf component cost by more than a factor of 2, maybe almost a factor of 3. How is that feasible? Are you shifting parts from off-the-shelf to custom?
The
Or
main
do you
reason,
anticipate
yeah,
being able to buy them much more cheaply than what you bought them for the prototype?
some parts are going to be switched from off the shelf to custom. And in addition, our custom parts are going to be actually like by percentage wise more expensive because like we said on our last slide, we're going to shift some of our 3D printed parts into metal ideally. And some of our parts, we actually had like one very expensive gear that was taking up most of our custom price. So those certain parts would become much cheaper when we order them in bulk. So that's just kind of the difference that we were able to calculate based on our estimated bulk prices and different parts that are going to shift certain materials.
So
All right, and so even with that, if you were able to, build your custom parts for 0 cost, right? You're still over your target of $100 per meter squared of reflector, right?
yeah,
Right now you're 3.5 times above that. And then on your risk slide, you listed that as a medium severity.
that is correct. Yes.
That seems more than medium.
The main reason why we said it was medium was because there's no really estimate that we can have, especially for the gears. Our main cost drivers on the assembly are all the electronics and the gears. However, if we account not really for 3,000 modules, but for the whole field of heliostats that we would be, or like in theory, we would be building, we're considering about 10,000 NEMA 23s, about 40,000 NEMA 17s, motor drivers. So we do believe that our cost can actually go a lot more down. However, we didn't want to come here to the presentation with an estimate of just guessing a number that we can reduce. And also gears, something that Ronnie was talking about. We have one very expensive gear that we had to use because we couldn't cast it in lab. It was very difficult to get the mold done for that one. And that gear was actually reduced by about 10 times only by going to 3,000 gears instead of 1 on exometry, considering that exometry is already making a profit of those. So we do believe that all the gears can be actually reduced by a lot. All the cost of the gears can be reduced by a lot, which that would drive our OTS and custom parts actually a lot less.
Could you have adapted your design not to need a custom gear and just take something off the shelf?
Yes, so that would be actually one of the things. However, the gears that we found off the shelf were also around $200 for the ring gear. This is based on a McMaster part that we found. They do not fit exactly what we need, but it's a very close fit. And just to have an idea, the small gears that we have, the driver gears that we use on the NEMA 17 motors on each reflection assembly, those one cost about $19 each. So kind of like that's the level, that's the reason why our costs are so high, especially for the prototype.
Well, I'm trying not to focus on the prototype, but more on the mass production, right? Because again, you're 3.5 times above what your customer says they're willing to pay for this.
Yes.
And if Julie was here, she would be waving the biggest red flag she can find at that, right? That's unacceptable, right? If I'm a customer, I'm walking away and I'm just not doing the project at that cost.
Right. Yeah, there are a lot of chances to reducing the cost in that sense, especially with the electronics and the gears, which are our main drivers of cost. So,
are you guys not paying your machinist either for that prototype?
Those weren't considered to be costs that were incurred by us. They were technically costs that were incurred by the lab, but the only costs that we're considering are the actual purchase orders that we placed. However, of course, the TAs are paid on their time and things like that, but those aren't costs that we actually had to place an order for.
Okay. What was the biggest manufacturing lesson you guys learned from this as you go forward and look into your careers and you think about design for manufacture and stuff like that? You guys did some casting, so obviously that's a pretty big deal. We didn't used to do that in the lab. So what's the big takeaway for you guys?
So at least for me, it's that what we do in SolidWorks is not necessarily achievable in the lab. That was a big one. We had to rechange the design, especially for the control boxes, at least 5 times because we had a good design, and then when we actually manufactured the parts using sheet metal, our tolerances were very close to not being met, and it was just not working. So we had to rethink about what we can achieve, the type of tolerances that we can achieve, and the type of quality and features that we can achieve in the lab with the machines that we have to build the boxes to still make the prototype IP55 and still make it work while doing it in the lab. So at least for me, that was a huge like experience in this semester.
And also from the talking about the cost, I feel like a lot of the metals piece we actually use is because we need to make it IP55, but a lot of them, if they are manufactured in a more like accurate way, we probably won't have to design it in this way that we can use actually less metal. So that's definitely gonna like lower the cost in this way as well.
Did you guys talk to Alon at all and of the TA that was machining for you guys and kind of get their perspective? Because I found like when I TA'd for this class that we would have these like really crazy parts that students would send through, and then they'd say, "Oh, we'll change it next semester." Then you know, things would never change. It'd be the same problems over and over and over again. And a lot of times it was an investigation of like, well, we'll talk to the machinist. Then you guys never did. So I just want to make sure you guys like actually talk to like Alon and the other machinists that are there and kind of get their perspective on it. I know I'm like harping a lot on the machinist standpoint, but that standpoint really matters like day to day, like mechanical design. So
yeah, we actually did. We were working almost hand by hand with the TAs in the lab. We had our first design was not talking to the TAs, and that was, I guess, the biggest issue at first. And then later on, we did talk to them and got their perspectives on what should we do. And we actually ended up like even being present, watching them manufacture the parts for our project. And as soon as they were done, like we would take the part and like take it to our table to start building. So yeah, we did have a huge connection and interaction with the TAs of class in the lab for building this module.
I will say that we spend, at least by the end of the semester, we spend hours talking to the TAs because whatever we made or we designed, we will say like, hey, is this possible? Am I being realistic? And then they will be like, no, you need to change this because I won't be able to make it. So then back to the computer, back to drawing, and figure out how to make it so that way they can do it with the lab resources.
Also, like required tolerances we needed on some parts. Some of the TAs like reminded us that higher tolerances are more expensive and take more time, and they don't really want to take the time to do all the tolerance. Like they don't want to get it so precise as we may need. So we have to design around that to be more cost effective.
All right, I've got the last question then. So you guys did your heat transfer analysis, and I know these particular ESP32 boards do not have a built-in temperature sensor, but at least last semester we required the students to build in a temperature sensor into their boards to measure internal temperatures. So how, A, did you do that? Do you have a way of measuring the board temperature? And B, how accurate was your heat transfer calculation in steady state temperature for operating conditions outside?
So unfortunately, oh, okay.
Go ahead, Daniel. Go ahead. No, that's fine.
Unfortunately, we forgot to include the temperature sensor, and we remember like right before classes were about to end, so we couldn't include it when we remember. And yeah, we did need to improve our heat transfer calculations because we experienced some overheating or some funkiness of the drivers while we were testing.
Yeah, so to extend on that a little bit, the biggest thing that we have is that on the analysis, we are making that heat transfer, we're making the assumption that heat transfer will happen outside the box. However, considering that we are in Florida and we are at about 90 degrees Fahrenheit, heat transfer is actually happening inside the box, not outside the box. So, especially at the beginning. So, you know, once the drivers start getting to a high temperature, we would be actually going to, you know, be at the level of almost a steady state. While the drivers and the motors are heating up, we will reach a steady state with the outside temperature, meaning that there's no heat transfer outside the box. So that means that we're only getting hotter. So one of the measures that we actually discussed as a group was to implement insulation systems, like passive insulation in the control boxes. However, we do wish we had a little bit more time to perform more testing on the module. At the end of the class, at the end of the semester, we were able to build it and test it on its functionality. However, we would like to, we would like to have a little bit more time to extend the testing and do, for example, heat testing, with wind testing, stability testing with the actual prototype, instead of just, you know, basing all of our studies in the hand calculations that we did. So with that, we can say that on Florida environments, the prototype might not work for summer, especially when temperatures get extremely hot in the upper 90s. But if we implement insulation, we might be able to get away with creating or dissipating the heat inside the box into the walls of the control box instead of keeping it inside.
Will insulation make the problem better or worse?
Well, that's what I was thinking, because insulation would actually keep the heat inside the box, but would not allow the heat of the outside to go into the box. But because we can actually have a huge contact area on the walls, because our boxes are pretty big, or especially the main control box is pretty big, we could actually use that as heat sinks, in which all our electronics are adhere with thermal glue to the walls, making all the wall heat up instead of just the electronic. In that way, dissipating. And then we would be able to, like, if we had more time, we would be able to measure possibly if there is heat transfer outside the box, not necessarily considering the temperature, but all the temperature of the outside environment, but also the wind going outside, dissipating this heat. So we do have ideas of what could work. We just need to test them in that sense.
Got it. Okay, thank you. There's another semester coming up. You guys could all just extend your stay at UF for fall, and we can keep going if you want. Anyway, so on that note, we're actually almost 15 minutes over. I did alert the next group that we're going to start a little bit late, but we're going to be eating into the break time. So so let's wrap it up there. I want to thank you guys for a whole semester of hard work, late nights. We took what were we at, TRL 4, and I think we made our way up to TRL 5. A heliostat that works in an outside environment where it's not protected by the air conditioning and the lack of bugs and lack of dust in the lab. So I appreciate all the effort and time that you guys put in, and the excellent presentation. So thank you, and we'll wrap it there. So let me hit the record button to stop things.
So Dr. Trump, before I do want to acknowledge the chat, Elise from Cummins, she mentioned something about the animations and the gears in lab, and we really appreciate your feedback. And yes, that is something, fatigue is something we did not consider, especially wind, for wind and the movement that the PVC arms will have. That is something that we would have to consider to fully validate the design under the outside environment. So we really appreciate that feedback as well.
All right, very good. Okay, so let's wrap it there because we're now way over time. So I'm gonna stop recording.